So the second difference here is all about aerodynamic heating. Aerodynamic heating. Let's bring in our good old reentry vehicle model. So some astronauts are coming in. You know, they got kind of this shape here. Looks kind of like a Hershey's Kiss. I'm hungry. Thanks a lot, guys. Thanks a lot. Okay. And I got my shockwave out the front. It's a nice bow shockwave. I've got a Mach number that's somewhere around 36 because it's going ridiculously fast. And the temperature of the air that's going through is around about 258. Okay. So pretty hot. Pretty incredibly hot. Woo! And there's an issue, though. There is an issue. Because the temperatures we'll be seeing after this shock wave are somewhere on the order of 11,000 Kelvin. But that's not actually what we would get if we use our calculations. This right here is accurate. However, if we were to actually go to our textbook, so we go to Appendix B, and yes, let's see here. And we would get that for a Mach number that's equal to 36, we would get that the Ts over T infinity, so the surface temperature over T infinity, is going to be equal to 252.9. And if we were then to calculate it, we would get that Ts is equal to, that's T surface right here, S. Be somewhere around, I don't know, 65,248 Kelvin. This is inaccurate. And it's also hotter than the surface of the sun. Woo! You know, just know the sun is around 11,000. Okay. But why? Why is this inaccurate? Well, it has a very simple answer. The answer is that because that's for air. And my computer's frozen. There you go. So this is for air. Now, you might think to yourself, well, don't I have air? No, you don't actually. So if we go just to like each of these guys breaking apart. So, you know, once again, we're going to draw this guy right here. And we have our shock wave. On this side, we have air. However, at 11,000 Kelvin, that's the accurate number, remember. Several things have already happened. So first off, oxygen is usually molecular oxygen. Well, that's already broken apart into 2O, which is just two oxygen molecules. That's very, very reactive. So, and that happens somewhere around 2000 Kelvin and is done by about the time that we reach 4000 Kelvin. Okay. Second thing is that nitrogen is also usually found in its molecular form, and it's going to break apart as well. And that happens somewhere around 4000 Kelvin. And it's pretty much done about the time I get to 9000 Kelvin. By that point, it's all broken apart. And then finally, even beyond that, nitrogen and oxygen are both going to ionize, which means that an electron is going to pop off because they have so much energy, and they're going to have this neutral because there's an equal number of electrons and ions, but this gas is made up of all these charged particles. And that happens somewhere about, with temperatures that are more than 9,000. So we no longer have air. This is plasma. And even at lower speeds, I still have a flow that is now chemically reactive. So it's chemically reactive. Because that nitrogen and that oxygen, they want to react now because they've broken apart. They went from their stable molecules to unstable single atoms. Okay, so the second difference here, the second big difference, is that we have a chemically reacting flow. So tables no longer apply. Okay, so this is what breaks us apart from supersonic flows when we go to hypersonic flows. We have viscous interactions, we have a chemically reacting flow, and that changes everything for us, absolutely everything for us.